Okay, so last lesson we covered constraints shortest path first, and what we discovered is that we're able to cause RSVP to calculate a path for us based on certain requirements, or what we would call constraints, that we specify. And what we found is that we can calculate a path based on the fact that the path must transit a certain router or certain routers on the way to the egress. We discovered that we can specify a thing called link affiliation, where we will classify our links, and we will say that the path must transit certain links based on the classification. And we found that it's quite common to use colours as a method of classification. So we have gold links, or silver links, or bronze links, and we can say things like, well, this path is allowed to use any gold or silver links, or this path is not allowed to use bronze links, or this path has to use all the gold links. So we can do things like that. We can also specify a bandwidth reservation on a path. We can say, well, this particular path, I need 20 megs of bandwidth on this particular path, or 100 megs, whatever it is that path required. So we got to specify some requirements, and then what we discovered was that RSVP would consult the traffic, our constrained shortest path first algorithm would consult our traffic engineering database and come up with an explicit route object, which essentially is a path segment, and it would then pass that across to RSVP to then build that label switch path based on the ERO that was calculated. So we discovered that we can use constrained shortest path first as a traffic engineering tool. But one of the great benefits of it, probably even a greater benefit than that, is its ability to protect traffic against network failures, which could simply be a failure in a link between 2 points. Maybe something's happened to the cable in between those points. Maybe there's been a device failure, maybe a router's gone out, maybe an interface has failed. So we can protect against link failures in between 2 different points, and a CSPF algorithm can calculate alternate path and reroute traffic around the failure very, very quickly. So what I want to do today is I just want to take a look at some of the mechanisms that are available to protect against those types of failures. Let's just, first of all, we're going to take a look at what happens when a failure occurs without any specific protection mechanisms applied, and then we'll take a look at what protection mechanisms are available and how they affect the time to recovery, or how they affect the mitigation of that failure once those protection mechanisms are in place. So we're going to take a look at the default traffic behavior of RSVP signaled LSPs. We'll look at these primary and secondary paths. I haven't really got into secondary paths so far, but we'll discover that we can configure secondary paths for a label switch path. So an LSP can have more than one path that we set up for it. In fact, we can have a primary and multiple secondary paths, as we'll discover. We'll look at how priority and preemption operate. So we've talked a little bit about priorities of label switch paths. And we'll take a look at that in some more detail. Look at the configuration and operation of a functionality called fast reroute, which is a protection mechanism. And we're going to look at the configuration and operation of link and node protection, which is a different protection mechanism. And we'll just talk a little bit about those two and kind of what the differences are and where you may need to use one or the other in a particular situation. And then we're going to look at label switch path optimization options. So this becomes, those optimization options are particularly relevant when you've got a lot of label switch paths on a network, and they're all competing with resources, and you have a changing environment where some paths are being established, some paths are being torn down, and we'll just take a look. How do you optimize that environment where you've got quite a lot of paths going on? So first of all, let's take a look at what happens. What just happens when what we've done is we've come along and we've signaled up some label switch paths. We're using RSVP to signal the paths for us. We're using CSPF to calculate the EROs for those paths for us. We'll work out a best ERO for a particular path. What happens if something goes wrong? What happens if the path fails? Well, there's a few things that occur or that need to occur before we can restore a path. So essentially the biggest problem is though, is that traffic that's in the path already will be dropped. And that any traffic that enters the path until we get this issue sorted out will also be dropped. So what we end up with is downtime. So you may have noticed that actually. Remember when last week we were signaling up our paths? It can take a bit of time for a path to come up. You might remember one path was signaling up there. It took about a minute for that path to actually go live. At least a minute. So let's take a look at what happens here. So basically, if there's a link failure, let's go back to this one here. So we have a link failure. So this link failure here is between R3 and R4. So there we are, we've got this failure has occurred, traffic can no longer reach the egress LSR. So R3 determines that there's a link failure between R3 and R4, and packets traversing the LSP are then now being dropped at that point. So R3 sends a reservation tear message upstream towards the ingress router, which is as a notification of failure. That message then heads upstream. R1 gets the message, R1 reacts to the reservation tear message for the LSP, and the path and the reservation state blocks for LSP are removed. So all of the mechanisms to reserve that LSP are then removed from those routers. So RSVP achieves that particular functionality. So then RSVP goes and tears those down. Also the route, the LSP route is removed from the INET.3 table. So the significance of that is that it's that particular route in the INET.3 table that allows BGP to resolve the label switch path as the next hop. Okay, so that is the route that BGP uses for its recursive lookup to say, I've got my next hop for my BGP session is that label switch path. So R1 will then attempt to build a new LSP by sending a path message downstream, and while all this is going on, packets continue to drop. So first we've got the process of, we have an error, let's pull the path down, and now we've got the next process of, now let's build a whole new path. So the process of even building a new path and getting that up can take a minute, maybe more. It doesn't even include the time it takes to tear down the old path first and recognize that there's been an error. So this is not a fast process. Okay, so a new LSP is established around the failed link. LSP route is added back into the INF.3 table. A little note here about the layer 2 and layer 3 VPNs. We haven't covered those yet. We're going to be covering those in our next lesson. We'll be covering layer 2 and layer 3 VPNs. But the really important point here is that traffic cannot traverse those VPNs, or traffic is being dropped across those VPNs as long as the level 2 path is out. So this whole process of recognizing there's an error, tearing down the path, you can see that, tearing down the path, establishing a whole new path. This whole process is a big problem if one of the services that you're providing to the customers of the Internet Service Provider, one of the services that ISP is providing to its customers is VPN connectivity, and with that you've always got service level requirements around that. You've always got uptime requirements around these sorts of things. So what you end up with is a potential breach of a service level requirement within a link failure. So this is very bad. This is something apart from the obvious inconvenience to your customers and unhappy customers. So it's obviously a very bad situation where we lose a link and it's going to take some time to come back up again. I mean, we might be talking about a minute, a couple of minutes here, maybe a little longer, that this whole link is out before we can signal another link to come up. So we're really talking about a number of minutes in this process to get a link back up and running again, because we have to recognize that there's been an error. The error has to be signaled, a new path has to be calculated using CSPF. RSVP then has to signal that new path. That new path has to then come up. A route has to be reinstalled back into a routing table, talking about VPNs, and all this process has to happen before connectivity is re-established. We're talking about at least 2 or 3 minutes, maybe longer, depending on the circumstances of topology. So it's taking a bit of time. So packets are lost while all this whole process is going on. So yeah, like an outage of say 5 minutes is quite significant in a customer's VPN. So that's the problem. So we had a look at the problem. Let's take a look at some of the things that we can do about that. First of all, let's take a look at this idea of secondary paths. So primary path is optional. We don't have to specify a primary path. We can have up to one primary path though. And if it's configured, the EROs will dictate the physical path for the LSP. If you don't configure an explicit route object, then we'll just end up following the LGP's best path. One of the things that we can do with a primary path is that if we do lose our primary path and we end up using a secondary path, so we do a failover to a secondary path, we can set up some mechanisms around what we're going to allow, or when and how we're going to allow a reversion back to a primary path. Ultimately what happens is, if we do fail over to a second path, the CSPF algorithm will attempt to recalculate the primary path, taking into account the failure. So it will try and recalculate a primary path that meets the goals of the primary path using the available topology that we have after the failure has occurred. So we have some mechanisms that we can control, things like how often do we try and bring this path back up. The default is every 30 seconds. How often are we going to try to bring this path back up? The default is unlimited. We just keep trying and trying and trying and trying forever. you can set a limit there. The revert timer is the minimum time the primary path must be up and stable before we fail over back to the primary path after having failed over to a secondary path. And the default is 60 seconds. You can control these things. If we set a 0 on that, it never comes back to the primary path. So we'll just stay on the secondary. Okay, so those are all these things are configurable, and there are defaults built in if we don't configure anything different. Okay, so secondary paths, 0 or more secondary paths. So we're not limited to just one secondary path, we can have multiple secondary paths. All secondary paths are equal, you can't prioritize one over the other. However, they are activated in the order in which they're configured. So we'll try the first one on the list. Can't get that one to signal up, and try the next one on the list. Okay, so we have a standby option for a secondary path, and what that means is that the secondary path will actually be signaled up. So in other words, instead of just sitting there as a possible path, and then we have a failure on the primary path, we then fail over to a secondary path, and we then signal up the secondary path and then fail over to it. You can have a standby option so that the secondary path is pre-signaled, so it's already up. So in other words, what happens is for our latest switch path, we have our primary path active, that is signaled. That's where our traffic is going. But on top of that, we've also got another path which we've already signaled, which is already up, which is already active. And it's just sitting there waiting for the possibility of the primary path failing. And then if the primary path fails, then we'll fail over to the secondary path. So secondary paths are a protection mechanism in that they do give us another path that our LSP can use if the primary path fails. So we're not waiting for a new primary path to be signaled before we can re-establish our LSP connectivity. We've got a secondary path ready to go. So we can have these secondary paths already signaled up just using the standby option in the configuration, which eliminates the time it would then take to signal up the path after the primary one fails. Of course, we do have to maintain that additional state information, so we are using resources to do that, but that's okay because it reduces the signaling time. Alright, here's the configuration for that. So we've got our latest switch path, switch path green, there's our egress there, 192.168.2.2. Primary path name is path 1. We specified a bandwidth of 35 meg on that path, and we've put a priority on that path. We'll get to priorities shortly and discover what that's all about. And then we've got a secondary path, which is path 2, and notice that we have got no bandwidth on that path. And you don't have to, you could put bandwidth on that path if you wanted to. However, it's a usual practice that you have less constraints around your secondary path than you do on your primary. Why is that? Well, because we're in a failure situation. We've lost a path. We just want to get another one up as quickly as possible, and we're not going to be so particular around what we need in that secondary path. We're just kind of happy to have a path at that point. So we're going to be less particular about what we might need on that path, because ultimately what our goal here is, after our primary path fails and we have failed over to the secondary path, our ultimate goal is to re-signal our primary path again, meeting our constraints that we've put onto our primary path, and then to revert back to our new re-signaled primary path. So the secondary path is kind of there to be used while we're trying to re-signal a primary path. Of course, you can configure it so that it never goes back to the primary path. That is certainly possible to do that. but the default behavior is that it will try, that there's that the CSP algorithm will try to find a new primary path and hand a PRO over to RFP to signal up that new path. So we can put other requirements on our paths, strict routes, etc. Okay, so what have we discovered? We can have a primary path, we can have a secondary path, we can have more than one secondary path as well. We also discovered that the default behavior is if our primary path fails, we'll fail over to the secondary, but then try and re-establish the primary and revert back to the primary. Okay, so path selection, the default is automatic path selection. If it's up and stable, the primary path is active. If not, the secondary paths are tried in the order in which they appear in the configuration. There are some things that you can do to change the default behavior. There's a parameter called select manual, and there's a select unconditional. So you can use one or the other on our primary path. Select unconditional just means that that path will be selected whether it's up or not. So probably not a great choice. So basically, even if it's down, it still gets selected. Select manual, the path is selected as active if it's up and stable. So the traffic reverts to the path based on the retry timers, retry limits, and the revert timer. So that's kind of what you probably want to happen is if we can get the primary path back up, we'll revert back to it. Okay, so a few things to check here, what we've discussed so far. How do you configure an LSP that does not revert back to the path that has failed? Well, that really comes back to, let's go back and take a look at that. This comes back to these primary paths here and the little things that we can tweak here. So we've got some defaults, we've got some things we can change. And really it's the, if you look at this revert timer here, the default is 60 seconds. So if the primary path is up for 60 seconds, we'll revert back to it. But if we can go in and set our revert timer to 0, which means we never go back to our primary path. So we can change that so that if we lose a primary, fail with the secondary, we just stay on the secondary. And the other question that we looked at here is what happens when 4 secondaries exist and the first one fails? Well, what we discovered is that secondary paths are signaled up in the order in which they are configured. So if we lose the first secondary path, we'll just go to the next one in the list and signal that one up. And so on. Of course, if you've only got the one, well, we are stuck. All right, so let's have a look at this here. This is the first answer to the first question. And setting our revert timer to 0, which means that if that primary path did fail, we're never going to go back to it. We're going to stay on the secondary. Okay, so what have we discovered so far? We've discovered that we can add secondary paths to our LSP. Why would we add secondary paths to an LSP? So that if our primary path does fail, we will fail over to the secondary path. We've also discovered that we can set a secondary path to standby, which means that the path is already signaled up before we have a failure. So not waiting for a failure, then say, oh, we've lost our primary path, better signal up the secondary path. So we can create a secondary path, we can specify that it will be in standby mode, and we can have that path signaled up ready to go in the event of a failure. Okay, let's take a look at these priorities. We get to put a priority on a path. So we have path priorities and look at the idea of preemption. So here's the point, is that an existing allowable switch path can be torn down to make room for a higher priority LSP. And where does the priority come from? Well, that's configured by the administrator. Okay, so configured by you, in other words. So you can say, well, a particular path will have a higher priority than another path. And you can decide what that might be. There may be certain paths which absolutely must always be there, and you can't really allow them to go down. They're your top priority paths, and maybe other paths that you will accept maybe some disruption in the path that you may allow it to go down and then have to be reconfigured or re-signaled. So you can put these priorities on paths. So let's take a look at a couple of concepts here. There are two things we said. We can put a setup priority, we can put a hold priority. So the setup priority is used when the path is being established. And what that setup priority does is it looks at the available bandwidth, looks at the bandwidth you have asked or you have requested, and if it gets to a situation where the bandwidth is not available that you've requested, then what it does, it looks at the LSPs that already exist and it looks at their hold priority. Okay, now, if the existing LSPs have a hold priority that is lower than the new LSP's setup priority, then that new LSP may tear down the existing LSPs to allow it to be established. So let's take a look at these priorities. The priorities values range from 0, which is the strongest, to 7, which is the weakest. So we have 7 possible priorities. Default priority settings, so if you don't set anything at all, the priorities that are set by default is the setup is 7 and the hold is 0. What does that mean? The setup is the weakest possible and the hold is the strongest possible, which means that no LSPs can ever be preempted by any other LSP. So no new LSP can ever tear down an existing LSP. And that's the default. Okay, now you get to change the default. Of course, you can configure that. So the LSP's hold priorities is one of the requirements when you are configuring priorities. The hold priority must be equal to or stronger than the setup priority to prevent preemption loops. Imagine if that wasn't the case. Imagine if the setup priority was higher than the hold priority. You could get a situation where the LSP could be set up, but then another LSP with a higher setup priority than that LSP's hold priority could tear it down, and then that LSP's setup priority could be higher than that LSP's hold priority. It could build it again, and it could be torn down again, and build again, and torn down again. So that could just keep on happening. So to prevent that, the requirement is that the hold has to be stronger or equal to the setup. Okay. So the way that if you're signaling up LSPs, the higher priority ones are signaled first and receive optimal paths. Now, you might think, well, this is a bit of a problem. You've got certain LSPs that have the ability to tear down other LSPs. that can't be good, because then the traffic on those other LSPs was going to be dropped. And you'd be right, that is exactly what would happen. To overcome that particular problem, we have a soft preemption configuration parameter. And what that means is that even though a higher priority LSP could potentially tear down an existing LSP, what the soft preemption does, it means that the existing LSP will first be re-signaled on another path before it is torn down. So it will be rebuilt somewhere else, and then it will be torn down. So that then prevents that situation where you start dropping traffic because an LSP has been torn down. Okay, so soft preemption is the configuration parameter that requires the LSP, if possible, to be rebuilt, re-signaled elsewhere before it is torn down. Okay, so let's take a look at preemption. This is look at the show PLS LSP extensive command. You'll see here that we have got an active path. This is secondary. So what's happened here is that the primary path has been torn down, and we're now using the secondary path. You can also go down and see that the session was in fact preempted. So what's happened is that the primary path has actually been torn down due to preemption, and we're now using the secondary path. Okay, so that's just an example of where that information can be found. Show MPLS LSP extensive. Okay, so let's take a look at this concept of setup and hold priorities. Setup and hold. So we've got a number of paths here. We've got at the top, we've got a green path with the setup 0 and the hold as 0. We've got a purple path, setup is actually the hold is 0, setup is 0. Purple path where the hold is 6 and the setup is 4, and we've got a blue path where the hold is 7 and the setup is 7. So now we've got a new path coming in, being configured, which is the red path. So we've got a hold of 6 and a setup of 6. So looking at that scenario there, which of those paths could be preempted by the new path, or the new red path? So we've got the green path, the purple path, and the blue path. So green, we've got setup and hold 0, 0. Purple, we have got the hold being 6, setup being 4. And the blue, we've got the hold being 7 and the setup being 7. And a new path 6 and 6. Okay, looking at that, which ones can get torn down? Okay, so what's stronger? 0 is stronger than 7. So 0 is the strongest and 7 is the weakest. Okay, so what we're looking for is a number that's higher than 6 in the hold. Purple. So the hold, so this is 6 is the hold and 4 is the setup. Okay, so 7 is the hold, 7 is the setup. So what it is, 6 is actually stronger. So the 6 setup is stronger than the 7 hold. Okay, so it is actually in fact the blue part that's going to be preempted there. Okay, so an issue there was that all the links with existing LSPs have less than 10 meg. So we've said must have 10 meg bandwidth, and we don't have 10 meg left on any link. If we did, were to just go ahead and build that, it wouldn't preempt any of those LSPs. But because we don't have 10 meg available on any link, and this is a higher priority LSP, it has the ability to tear down an existing LSP for built. Right, so in this case, it would tear down the blue LSP. Okay, so we looked at the concept of primary and secondary LSPs. Looked at the concept that we have priorities. Looked at the concept that we have a setup priority and a hold priority. That the hold always has to be at least as strong as the setup, and that in our priorities, 0 is the strongest and 7 is the weakest. And that some LSPs are able to preempt or tear down other LSPs to allow them, those LSPs to be signaled. All right, now let's take a look at traffic protection in more detail. So we looked at, first of all, we looked at a secondary path as a traffic protection mechanism. One of the problems, though, with the secondary path, as we'll have a look, is that it's actually still quite slow. So, and the question is, how can we make this faster? So with the secondary path, we've still got to recognise the failure, we've still got to signal the failure up to the ingress LSP, and then the ingress LSP has to then fail over to the secondary path. If the secondary path was not in standby, it has to signal up the secondary path and then fail over to it. So all that can take a fair bit of time. We're still talking about a few minutes here for this to happen. Okay, so without a secondary path, maybe we're talking about 5 minutes, maybe we're talking about more. With a secondary path, okay, we're still talking about a few minutes, maybe we're talking about 2 minutes now, instead of five or more. So how can we make this faster? Because the problem is we're still losing data, we're still dropping packets with this situation. Is there a quicker way? Is there a quicker way to fail over in the event of a primary failure? How can I reduce packet loss when I lose my primary LSP? Okay, so the answer is this fast reroute. And this is defined in RFC 4090. It is this what's called a one-to-one backup method. We'll take a look at how it works. And it's to protect when a link or a node or link fails. Okay, so if a particular node or link fails, then the upstream node will detour around the failed downstream node. So we'll get an immediate detour. And it will also signal the failure up to the ingress LSR. Why does it do that? Well, because ultimately the ingress LSR is going to have to recalculate a holding path that satisfies the constraints applied to that particular path. So this fast reroute is a short-term mechanism that's going to allow us to maintain connectivity while a new path is being signaled up and established. So it is a short-term fix to prevent packet loss. Okay, so let's take a look at these characteristics here. It's only the ingress LSR that knows all of the traffic engineering constraints. So the ingress LSR computes an alternate route based on configured secondary path and tries to re-establish the primary. So as we've said, this is the default behavior. So when we get a failure, it will fail over to the secondary path and try and re-signal the primary. So this is initiating the long-term solution. So by default, the reroute detours inherit administrative groups only, so the detours don't honour the bandwidth, the EROs and so on. So this is talking about the reroutes now. So the characteristics of this reroute is that it's configured on the ingress router and it detours around a node or link failure. So the speed of the reroute is actually the really beneficial thing. Less than 100 milliseconds of reroute time after the failure is detected. Sort of the going sort of average on a reroute failure is around about 50 milliseconds. So how fast is 50 milliseconds? Well, there's 1,000 milliseconds in a second. Okay, 1,000 milliseconds in a second. On average, fast reroute takes about 50 milliseconds. Okay, so in the absence of fast reroute, we're talking about a number of minutes to re-establish a path. In the absence of the secondary path, we're going to be talking about 5 minutes or more to re-establish a path. With the secondary path failure, but we're still talking about maybe 2, maybe 3 minutes to re-establish our path. With fast reroute, we're talking about a very small fraction of a second to re-establish our path. So what we really are doing is we are avoiding data loss. We're avoiding packet loss on our path using fast reroute. So the detour paths are calculated and they are immediately available. So what happens is that we're going to, the TED, the Traffic Engineering Database, is going to be used to calculate the detours. And the beauty of it is that every node along the link is going to calculate its own detour. So we don't need CSPF LSP to be set up on the ingress node. Every node is going to calculate the detour. So let's take a look at this particular scenario here, where we have got an LSP set up. Our primary LSP is going from San Francisco, it's going through Los Angeles, and then it's heading out to New York over there. So it's basically going through Austin, Miami, and up to New York. So that's our primary path. Now there's our LSP. We're going to enable fast reroute on that. So what happens is that every router then pre-calculates in advance a reroute path around its downstream router. Now nothing's failed at this point. Okay, nothing has failed. All we've done is we've enabled fast reroute on that LSP. Okay, so nothing has failed, but every router along the path calculates a reroute path around its downstream. Okay, so it's still using the primary, it's not using the reroute path, it's just calculated the reroute path. Then if we do get a failure, what happens is the reroute path will be immediately used. So basically, let's go back to our previous slide. If a failure occurs on any downstream node, immediately the reroute path will be switched in. So the way that these reroute paths work is that they are pre-installed into the forwarding plane of the router. So they're basically already there. And the forwarding plane works in milliseconds in the speed of operation. So the forwarding plane will instantly a failure is detected, the forwarding plane immediately switches over to the pre-calculated detour, which is the reroute path, and traffic will then be routed through to the egress via the reroute path. Okay, so what we achieve is instant reroute, and we avoid packet loss. In the meantime, a new primary path or a secondary path, if a secondary path exists, a secondary path can be fail over to a secondary path, and ultimately we'll re-signal a new primary path. So this is the situation after reroute or after the primary path has failed. We've got a failure between Los Angeles and Austin. The fast reroute takes the path up through Phoenix, through Fargo, and out to New York. So that's the immediate response. That is a temporary response. Then what will happen is there will be a failover to the secondary path. Traffic will then fail over to the secondary path. The primary path will be totally torn down at that point, and then ultimately resignaled. So there's our. So initially, the primary path stays up with the fast reroute in place. Secondary path is signalled up, and traffic is then failed over to the secondary path, and eventually the primary path is taken down, and ultimately resignalled. Okay, so that's the parameter there, the configuration parameter. Fast reroute is added into the loader switch path. Applies to all primary and secondary paths. Okay, we can take a look at the operational command there, show LSP extensive, and there is our fast reroute desired. So that tells us we have configured fast reroute on our LSP. Okay, so this is great, great protection, particularly if you're protecting a particular customer's VPN, for example. You put fast reroute onto a customer's VPN, which means that if there is a link failure, that customer will not lose data. So they will immediately get fast reroute, will kick in, data will not be dropped, and ultimately, if you configure the secondary path will become the active path, and traffic will be then forwarded down the secondary path, and traffic will not be dropped in that process. Okay, so you are protecting the path, you're protecting that particular circuit for that customer. Okay, that's a very important point if we're using, if you are relying, or if a customer is relying on a service provider for its VPN. Okay, that would be something, if you were a customer, that would be something that you would be interested in asking about. What protection mechanisms does your service provider provide to you as a customer? If you're saying, look, someone's saying, well, we'll offer you a VPN service for you, we'll connect your sites together. It'd be interesting for you to know what protection mechanisms does that provider implement to protect your VPN. Do they use something like fast reroute to protect your particular VPN? Okay, that's just an example that detour is up. And this is taking a look at the route. You can see this parameter here, detour is up, means that fast reroute is actually been activated. We've had a failure, and the detour is now active. So we're now routing the traffic along the detour path. Okay, one other little thing that we can do to tweak, just another little tweak on the fast reroute topic, is that when you do have a failure, the new path has to be installed into the routing table. What you can do is you can pre-install that in the routing table using the load balancing option. And so you can essentially load balance that and put the other path in there, ready to go, so that it's basically instantaneous. If that failure occurs, the reroute is basically instantaneous because the other path is already installed. Okay, so that was let's just take a look at fast reroute. So what did fast reroute do? It protected a labeled switch path, okay, by pre-calculating in advance the detours around downstream nodes, so if one of them fails, the detour is ready to go. Hit it and reroute straight around it. Okay, so as I said, that happens in a very small fraction of a second. On average, it's around about 50 milliseconds. It's 1,000 milliseconds in a second, right? So it's a very small fraction of a second, as opposed to a number of minutes if we're just waiting for a new path to be signaled up. Alright, so let's take a look at another mechanism that we have available to us, which is bypass LSPs. Okay, so these are LSPs which will bypass a downstream failure. Protects interfaces instead of an entire LSP path. So this is the primary difference here between fast reroute and bypass LSPs. Fast reroute is specific to a label switch path. So its context is protecting an LSP. Whereas link protection, its context is it's protecting a particular link or a particular interface. So what is the difference between the two is that this mechanism here can protect multiple LSPs that use this particular link, this same link. Whereas fast reroute protects a specific LSP. So if you've got lots of LSPs that you want to protect, then with fast reroute you can figure the protection on each and every LSP. Each and every LSP calculates a fast reroute path or a detour path around a downstream node. Now if you've got a lot of LSPs that you're protecting, that is very, very resource intensive. It does not scale particularly well. If you've only got a few LSPs, it works very well. If you've got many LSPs, I mean in the hundreds, it doesn't scale very well. This particular approach, link protection, we're protecting a link, so it's centric to a link rather than to an LSP. So any LSPs that use those links can be protected by this mechanism. So if we have a link that fails, or even a downstream node that fails, we'll look at that shortly, all the LSPs that may be using that link or that node can be rerouted around this new path that we're putting in place. So what we can do here is protect multiple LSPs. Maybe we've got 100 LSPs that we're protecting on this particular path. So it scales a lot better. So really it's a case of how many LSPs are we protecting as to which approach you'll take here. So let's take a look at it. In the RFC 4090, this is called a facility backup. Okay, so Juniper call it link protection, that's kind of their name for it. The RFC calls it facility backup. Same RFC describes fast reroute, in which fast reroute is called the one-to-one backup. So this is in the RFC is referred to as the facility backup method. And so you've got to flag the LSPs to make use of the bypass label switch path. So you create the bypass and then you will flag certain LSPs that you want to be protected by it. So the bypass LSP is established around the protected interface to the adjacent node. So this is just what's called a link protection. So what we're doing is we're protecting, in this case, the interface on R2 that connects to R3, and also the link that goes from R2 to R3. I mean, that may perhaps be an optical fiber cable that could potentially span many parameters, which potentially could be damaged or dug up or whatever. Anything could happen to it, right? It's people sometimes do that, right? So it protects that link. What it does is establish this alternate path goes around that particular link, and that path is not active, but it's available in case the link fails. So the bypass LP is established around a protected interface to the adjacent node. Use CFPF to calculate the bypass LSP. Can add an ERO to influence the CFP routing of the bypass LSP. You can specify a path in the ERO. Okay, so node protection. So node protection is pretty much the same concept as link protection, except now we're protecting an entire node. So if R3 were to fail, we now have an alternate path that goes right around R3. So this looks a heck of a lot like fast reroute, doesn't it? Okay, but just remember that the context here is fast reroute is the protection of a particular label switch path, and a reroute path is established on every single router or by every single router in that LSP. This is centric to a particular link or a particular node. So what we're doing here is we're protecting the link from R2 to R4, and that protects this alternate LSP that we're calculating. So basically what it is, we're pre-calculating a failover path. That can be used by every LSP that has to use the link between R3 and R4. Okay, so not specific to a particular LSP, it can be specific to the link or the node that we're protecting, and it can be used by multiple LSPs that use that path. So this uses a similar mechanism to link protection, relies on RSVP hello timer to determine node failure. LSPs are flagged to make use of a bypassed LSP, and one bypass LSP is established around the downstream node. As I said before, that is then can be used by multiple LSPs that are protected by that. Okay, so by default, a single bypassed LSP is automatically created to provide link protection. You may specify a number of bypassed LSPs, automatically created using the max bypasses statement, the maximum on that. And manually configure individual bypass LSPs as well, so you have manual LSPs that you set up. Router will use the following algorithm to determine which bypass LSPs to use for a new protected LSP. Use any current active bypass LSPs that satisfies the bandwidth, link protection, no protection of the original LSP will be used. If no active LSPs are available, then scan through the manual bypass LSPs in order of configuration for a bypass LSP that can satisfy the requirements, and then automatically create a new bypass LSP if my max bypasses is greater than 0. Okay, so that's kind of the approach that's going to be taken. Configuration. So each protected interface, or node for that matter, is configured under the edit protocol RSVP hierarchy, and we can put a fair few constraints in here that we're looking for, so you can exclude certain administrative groups, include administrative groups. This is our links, our as the classifying our links. Put all those constraints in, put a bandwidth in, and give it a name, and what the bandwidth is going to be. We put in strict and loose hops, and we put in the egress of our bypass LSP. Max bypasses, default is 1. Okay, so all those things are possible. The minimum configuration that you need is over on the under RSVP. We'll just put link protection. Just going to put that statement in there. So and then the defaults will apply. Then we go over onto our MPLS. So we apply it to an interface under RSVP. And then over on MPLS, you then apply the link protection or node link protection, which means it protects the node and the link. And you then apply it to the label switch path. So we're setting up link protection under RSVP on the interface, and then we're saying what actual LSPs are going to use that link protection. Which LSPs are protected by that link protection LSP that we're putting in place. It's a bypass LSP that we're putting in place. So we can have, let's go back here, but we can have multiple, we put multiple LSPs we can apply that link protection to multiple LSPs. Again, this is us checking it out. Show the RSVP interface extensive. We see that the link protection has been enabled on a particular LSP. And in this case, we can see the protection is on. We're using bypass 1, LSP 1 protected, LSP is 1, and we've got the details of the bypass information there as well. Okay. Alrighty, so that was I was taking a look at link protection. What I might do now is we'll take a short break, and when we come back, we're going to take a look at LSP optimization. And there's a few things we're interested in here as to how we need to tweak and optimize our LSPs, particularly when we've got all these extra paths, protection mechanisms in place. All this stuff is going on. We've kind of got a lot of bandwidth reserved by all this protection mechanism that we've got. How do we optimize all of this? How do we get the most out of our LSPs across our topology? We're going to take a look at that when we come back from the break.